Hello. In this video, we'll talk about another proof method. This is from section 3.4, which is proof by cases. So proving things by cases. So the idea here is, let's say we want to prove a statement like for all x in some set S, R of x. So here R of x is some open sentence over this domain S. And let's say we want to prove this. And now R of x, it could be an implication, it could be a conjunction or a disjunction of other statements, but for now we'll just assume it's just, some statement R of x. So it might be that we don't really have enough information about x to prove R of x directly. So for instance, let's look at a result that we're going to prove in a second. If n is an integer, then n squared minus n is an even integer. So, right, if we want to prove a statement like this, one way we could write this is to define the open sentence p of n squared minus n is even. And then another way we could write this, rather than as an implication, we could say for all integers n, p of n squared minus n is even. That's a perfectly fine way to express this statement. Even though it's an implication, we know that universal statements can sort of be thought of as implications themselves. So in this case, n is just an integer, and we want to show that n squared minus n is even. So we don't really have a leg to stand on here with n just being an integer, right? We don't have quite enough information to be able to get good leverage on showing n squared minus n is even. So the idea is to break this down into cases. In this case, we're going to break down the integers into the even integers and the odd integers. Now, once we know n is even, then we can write it as 2k, and we'll be able to show that n squared minus n is also even. And if n's odd, we can write it as 2k plus 1. And then we'll be able to plug it in here and hopefully show that this is even. So that, by breaking it down into more specific cases, in each of those specific cases, we'll have more leverage on proving the statement. In general, what this looks like is to give a partition of the set S. So for all x in S, R of x. So suppose, let's say S, let's give it like S1, S2. Let's maybe just focus on that case. Let's just say we have two sets here is a partition of S. So S1 is some subset of S. S2 is some subset of S. And we know that S1 union S2 is equal to S. And S1 intersect S2 is empty. There's no overlap between the sets. So given some partition of S, we can rewrite this. Once we know we have this partition, we can say for all x in S1, let me say equivalent here, for all x in S1, R of x, and for all x in S2, R of x. Now these statements are equivalent exactly because this is a partition, because the union of the two sets gives me all of S. What this allows me to do is take one statement, turn it into two statements, prove each of those individually, and then together they prove the original statement. Now in general, we might want a bigger partition. Or not a bigger partition, but a partition into more sets. S1, S2, S3, up through, in general, just sk for some integer k is a partition. The same idea will work. We'll have that for all x in S, R of x will be equivalent to showing that, well, for all x in S1, R of x, and for all x in S2, R of x, and so on until we get to k. x and sk are of x. So we don't just need to break it down into to 2. That's not our only option. We can break it down into a bunch of different statements and prove each one individually. For this first case, or I guess while we're just learning this, we're just going to focus on breaking it down into 2 sets and proving each of those. But remember that we have partitions like for the real numbers. Remember, we can partition this into the ones greater than or equal to 0. So x is in the real numbers. We could have x strictly greater than 0. Maybe for another statement, we might want to break it down to positive x's, negative x's, and x equal to 0. This would be an example of breaking down the set S into 3 subsets and considering each one of those cases individually. So we might encounter this later on. But for now, our main partition is going to be the evens and odds of the integers. And we'll turn our attention back to proving this statement. If n is an integer, then n squared minus n is an even integer. Okay, so this is our proof technique. Proof. And what we'll do here is specify the cases. So I'll say case 1. Suppose n is even. And now I'll go off of case 1. I'll say, okay, then n equals 2k for some integer k. So n squared minus n would be 2k squared minus 2k. So that's 4k squared minus 2k. We can factor out a 2. So that's 2k squared minus k. And now I've written it as twice an integer. So I can say hence hence n squared minus n is even. And that would prove case 1. And then I also have to consider the odd integers. So case 2, that is the other set in the partition. Suppose n is odd, then we would have n equal to 2k plus 1 for some integer k. And it's okay to reuse when you're doing cases, since these are sort of arguments that stand alone. It's okay to reuse symbols like k. It's not the same k from this case. We're not assuming that, because now we're in a totally different case. We sort of refresh all of our variables except for, I guess, n here, because that's what's defining our cases. So this is okay to do. N equals 2k plus 1. So again, we can look at n squared minus n. That'd be 2k plus 1 squared minus 2k plus 1. 2k plus 1 squared is 4k squared plus 4k plus 1. And then minus 2k, distribute the negative through, minus 1. So this is 4k squared. I'm gonna simplify this by combining like terms. 4k minus 2k, so that's plus 2k. And then I have 1 minus 1. Those guys cancel out, and that's really nice for us, because now we have 4k squared plus 2k. I can factor a 2 out of that. So that's 2k squared plus k. And now I have n squared minus n written as twice another integer. So n squared minus n is even. So in either case, n is even or n is odd, we've shown that n squared minus n must also be even. And we've proved it. All right, we'll see some other examples of this in the next video. I'll see you there.